All right, hello everyone. We are looking at chapter 7, it's titled Sampling Distributions, and in this video we're starting off at section 7.1, what is a sampling distribution? So, in the learning targets, by the end of this section you should be able to distinguish between a parameter and a statistic, create a sampling distribution using all possible samples from a small population, use the sampling distribution of a statistic to evaluate a claim about the parameter, distinguish among the distribution of a population, the distribution of a sample, and the sampling distribution of a statistic. Determine if a statistic is unbiased estimator of a population, and describe the relationship between the sample size and the variability of a statistic. So, we should be familiar with these two terms already, but a statistic is a number that describes some characteristic of a sample, while a parameter is the number that describes some characteristic about the population. So statistic goes with sample, parameter goes with population. For example, right, you could find the mean. If it's the mean of a sample, we use x bar. If it's the mean about a population, then it is mu. The other one that we should be familiar with is standard deviation. If it's of a sample, it's s sub x. And if it's the population, it is just sigma. All right. The new one we're going to look at, all right, is for proportions. If it is the population proportion, it is p. And if it's a sample proportion, it is p hat, right? So, like I said, statistics go with sample, parameters go with populations. And then note, a sample statistic is sometimes called a point estimator of the corresponding population parameter because the estimate is a single point on the number line. So for example, if I took the mean height of our class, right, that sample, that would be x bar, that'd be a point estimator for the true population, the mu of height for the school, because it is one specific estimator, one point, one sample mean that I found. So let's identify the population, the parameter, the sample, and the statistic in each of the following settings. The Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. So population is going to be all U.S. adults, right? Because that's where you sampled from. It's pretty easy to figure out your population because wherever your sample comes from. So population is all U.S. adults. The parameter then is P, the proportion of all U.S. adults who believe in ghosts. For my sample, I sampled 515 people, and they were interviewed by the Gallup poll. So that's what I know my sample is. And really, it should be 515 U.S. adults sampled by the Gallup poll or interviewed by the Gallup poll. And then the statistic from that sample, 160 said yes. So my statistic, I'm using it to estimate my parameter, which is a true proportion of all U.S. adults who believe in ghosts. So my statistic p hat is the proportion in the sample who say they believe in ghosts, and it is 160 out of 515, or 0.13. All right, for situation B, during the winter months, the temperature outside the Starnes cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperatures actually get in the cabin. A digital thermometer reads the indoor temperature at 20 randomly chosen times during a given day. The minimum reading is 38 degrees Fahrenheit. So here now, my population is all time during the day in question, all right, because I'm taking a random sample of 20 times throughout the day. So the population is at any time or at all the time in the day. The parameter is then the true minimum temperature in a cabin at all times that day. And then of my sample, the 20 randomly selected times, and my statistic, which I used to estimate the parameter, the sample minimum temperature was 38 degrees Fahrenheit. Right. So many students do lose credit on the AP statistics exam when defining parameters because their description refers to the sample instead of the population, or because the descriptor isn't clear about which group of individuals the parameter is describing. When defining a parameter, we suggest including the word all or the word true in your description to make it clear you aren't referring to the sample statistic. All right, so remember, when you are defining your parameter, you need to be talking about the population. And when you're defining the statistic, you are talking about the sample. I said S and S, P and P. Okay, we've talked about this briefly also, but it's going to come up a lot more now. So the idea of sampling distributions and sampling variability. Sampling variability refers to the fact that different random samples of the same size from the same population produce different values for a statistic. So let's take those heights again, right? If I'm trying to find the true average height of students at Naval North High School, I take one sample of 28 students in first period, and that's my one sample. I'd find a mean, and that'd be 1. Then I do it again for second period, take another sample of 28 students, and that's another one, right? Each one of those is a sample. Each one of those is an X bar. All right, there's one X bar in first period and an X bar in second period, and they're going to be different simply because of sampling variability. That the different samples produce different estimators. All right. The only way that you'd get the same answer for both is if you sampled the whole population and you actually found out the parameter. There's only one parameter, right? There's only one true height of all, or one true average height of all students at Naperville North. However, there's a lot of different sample heights depending on what class period you select or how your sample is taken. All right. So the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So, like I said, if this was our example from here, maybe this was first period's average height, and this one is second period's average height. All right. Now, if you wanted to build the sampling distribution of the mean height of all students at Naperville North High School, you would have to take every possible sample of 28, right? The sampling distribution is based on the same size sample, and it is every possible sample out there, okay? Now, if you think about it, if you had to make every unique sample of 28 students from Naperville North High School, there would be a lot of data points, all right? So we're not going to do that right now. Obviously, that would take way too long, but we'll look at another example here. But a sampling distribution is every possible sample of the same size. So there's multiple sampling distributions out there, right? About if we take our average heights question, right? The sampling distribution would look slightly different if I took samples of size 25, or if I took sample sizes of 40, or samples of 50. Each one of those would be slightly different because the sample size is determined, or it does dictate the shape of the sampling distribution and where each X bar falls. All right. But the important thing to realize now, we're no longer plotting one data point. All right. We are plotting, this is a statistic. This is one sample mean. This is one sample mean. This is another sample mean, and so forth. Each one of these is a sample mean because it's a sampling distribution. All right. So John and Carol have 4 grown sons. Their heights are 71, 75, 72, and 68. All right. So you want to list all possible sample sizes, or all possible samples of size 2. Okay. So I could have 71 and 75, 71 and 72, 71 and 68. Or I could have 75 and 72, 75 and 68, or 72 and 68. These are the only possible samples of size 2 with these 4 people. All right. And now I'm going to calculate the mean of each one. So I would just add them up and divide by 2. And I get all the means. And now I plot them. So if, so I then plotted each one of these. So each dot is a sample mean. This is 73 is right here. 71 and a half is right here. 69 and a half is right here. 73.5 is right here. 71.5 is right there. And 70 is right there. So each one is a sample mean now, and they're all of the same size too. So since they're all the same size, and this is every possible combination of size 2, this is the sampling distribution of John and Carol's 4 sons of sample size 2. All right, that's what the sampling distribution looks like. All right, now if we did it of ranges, right, because you can do it for any statistic you want. The first one was about means. The next one is a different statistic about range, right? The statistic is just dependent on what you measure, all right? Same thing with like your random variable. There's a lot of, you can do the same random process, and then you can choose what random variable you want to measure. Same thing here. You could have multiple samples, and then you just choose what to measure. Here we're going to measure the range of their heights. So we have 4, 1, 3, 3, 7, 4, and this is it. Again, since this is every possible sample size of size 2, it is the sampling distribution of their ranges. Okay. To determine how much homework time students will get in class, Miss Lin has a student select an SRS of 20 chips from a large bag. The number of red chips in the SRS determines the number of minutes in class students get to work on homework. Miss Lin claims that there are 200 chips in the bag, 100 of them are red, and that means 100 of them are blue. When Jenna selects a random sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half the chips in the bag are red? So, what is the evidence that less than half the chips in the bag are red? Well, we do have some evidence, right? She got 7 out of 20. So, right there, her sample proportion, 7 out of 20, is 0.35, which is less than 0.5. So, we do have some evidence that, hey, I got less than 50%, so I got less than half red. So there might be something fishy going on. Now the question is how strong is that evidence, right? We have some evidence, but how strong is that evidence? All right. And that is where the sampling distribution comes into play, because there's 2 possible explanations for what could happen with those 7 chips. Either one, it is possible that Miss Lin is telling the truth, and Jenna got a sample proportion less than 50% because of sampling variability, right? You just took this one sample and it just so happened that, hey, it was less than 50%, even though the actual split is 50-50. However, the other possibility is it's also possible that Miss Lin is lying and less than half of the chips in the bag are red, and that's why we got less than 50%. Like maybe the actual proportion is really 0.35 or whatever it was. 0.35. Maybe that is the actual proportion, and Miss Lin's lying to us. All right, but those are the only 2 options of what could occur for us to get less than 50%. So what we're going to do is we're going to need to make that sampling distribution to see, hey, how likely was it to happen? Did it just happen by random chance? Or is that actually pretty common to happen? So now think about it though. There's 200 chips and you're taking sample sizes of 20. That is a lot of samples to have to take. You need to take every possible sample size of 20 to make it. And think about it, when there was only 4 options and you did sample sizes of 2, that was already 6 options. If you have 200 chips and you need every possible sample of size 20, that is going to be a lot of data points. So we can't do that easily. So instead, we are going to use technology to simulate choosing 500 SRSs of size 20 from a population of 200 chips, 100 red, 100 blue. All right, and now the dot plot shows p-hats. They show individual sample proportions of red chips from the 500 samples. So each dot you see here is one sample proportion. All right, so we did 500, so there's 500 dots on here. Each dot is a sample proportion. So there's one dot at 0.8, and that represents in one simulated SRS at 20 chips, there were 16 red chips, which is 80% out of the 20. All right, so that p-hat for one specific sample is 0.8. So now using this sample size, would you be surprised to get a sample proportion of 7 out of 20, which is 0.35, or smaller in an SRS of 20 when p is 0.5? So we assume that p was 0.5, that's how we did this SRS, and 0.35, that's here, that happened quite a bit of times, all right? So there's many samples, right? There's a lot. You can't even see all the dots, but there's a lot of times where this occurs, right? Anything from here and lower, that happens quite a bit. So I'm not very surprised that I got one less than or equal to 0.35 because looking at the sampling distribution or the random samples of 500, it happened pretty frequently. All right. So based on the first answer, we had some evidence that she might be lying to us. But how strong is that evidence? Well, I would not say, um, I would say, since it isn't surprising to get a p hat less than or equal to 0.35, because again, that happened pretty often. All of these data points happen there. By chance alone, when p is 0.5, right? We did that based on assuming that p is 0.5. There isn't convincing evidence that there are actually less than half the chips in the pack that are red. There was that little bit of evidence at the beginning. However, it happens so regularly when there is 50% bags in the chips that I'm not surprised that I got a value of that one on my one specific sample. So this is an important thing to note. When we simulate a sampling distribution using assumed values for the parameters, like the chips example, the resulting distribution is sometimes called a randomization distribution. Um, So just because we use an SRS to generate it, because again, it would be very difficult to find each one of those in every single possible sample of size 20 here. The other thing to note is that it's important to realize that we assumed the value for the parameter. We went about this distribution assuming that she was telling the truth, that 50% of the distributions or sorry, that 50% of the distribution is red. We assumed that and we went about it making that assumption. Okay. So there can be a couple different distributions here. So this is kind of building an idea of a sampling distribution. So here is our population distribution again, right? We have 200 chips, 100 are blue, 100 in red. So my parameter is 0.5. My P is 0.5. Okay. I then go do a sample of size 20. And in one sample, hey, I got 12 blue, 8 red. So my P hat, let's see what it is. So this is one sample of size 20. This is another sample of size 20. Right here, I got 9 blue, 11 red. And I would keep doing the sample size of 20. So I'd get another one, and another one, and another one. And each one of those is the distribution of the sample data, right? It's just a specific p hat, all right? And if I did every possible size of sample size 20, then I could start building the sampling distribution. And the sampling distribution is where I take my individual p hats and I plot them on my number line. I make a dot plot out of them. Okay, so my p hat, which is 8 out of 20, 0.4, that's a dot here. P out of 11 out of 22, that's 0.55. Boom, that's right here. And so forth. And if I did all of the sample data, I took every possible sample size, 20, found my p hat and plotted it, then I'd get the true sampling distribution. Now, like I said, very difficult to do that. So instead, we have this approximated sampling distribution, but it still behaves the same way. Each dot is a sample proportion. Okay, so it's important to realize each dot is a sample proportion or a p hat. So the population distribution gives the value of the variable for all individuals in the population. The distribution of sample data shows the values of the variable for the individual sample. So this is at the very start. This is the true fact. This is what we're trying to estimate. This is confusing. We're essentially trying to estimate this, but here we know it's 0.5. Then I take a bunch of samples, all right? And the sampling distribution displays all those values of p hat from all possible sample sizes of the same size. All right? So population distribution, distribution of the sample data. Each one of these would be their individual, and then the sampling distribution of the sample proportion. So this is a big thing to note. Terminology matters. Never just say the distribution. Always say the distribution of blank or the sampling distribution of blank. You should always define your distribution. Be careful to distinguish the distribution of the population, the distribution of the sample data, and the sampling distribution of a statistic. Likewise, don't use ambiguous terms like sample distribution. All right, give it a specific name, because that which could refer to the distribution of the sample data or the sampling distribution of a statistic. You will lose credit on free response questions for misusing statistical terms. So be very specific when you define what the distribution is that you're talking about. Okay. A statistic used to estimate a parameter is an unbiased estimator if the mean of the sampling distribution is equal to the value of the parameter being estimated. So if we took all possible samples of 20 chips from the population, calculated p-hat for each sample, and then found the mean of those p-hats. So we take our p-hat, plot it. Basically, we get our sampling distribution of red chips. Right? That would be here. Now, if we found the mean of that distribution, we'd get exactly 0.5. All right. And that means that p-hat value is an unbiased estimator, because what it says is unbiased estimator if the mean of the sampling distribution, so we made the sampling distribution of sample proportions, found the mean of it, if that is equal to the value of the parameter being estimated, it's unbiased. So we knew the p is 0.5. So since the fact that our p-hat, when we took the mean of p-hat, it also equals 0.5, that means that p-hat is unbiased. Okay. So here's another example. In the sampling heights example, we created the sampling distribution of the sample ranges for samples of size 2 from the population of John and Carol's 4 sons with height 71, 75, 72, 78 inches tall. Is the sample range an unbiased estimator of the population range? Explain your answer. So the mean of the sampling distribution, right? This is the sampling range. We found all of them. So each one of these dots is the sample range. So there's 6 samples. We found the range of each, plotted them. So it's unbiased if the mean of this equals the population parameter. So when I took the mean of the sampling distribution, right, I did that just by adding up all the data points and dividing by the number. I get 3.67. However, the range of the population is 7, right? The range of the population, the way you'd find that is just your maximum height minus your minimum height. Since these are different, since the mean of the sampling distribution of the sample range is not equal to the value it's trying to estimate, which is the population range, right? The sample range is not an unbiased estimator of the population range. So if you take the mean of the sampling distribution and it's equal to whatever the population parameter is, that same one, then it's unbiased. If not, it's a biased estimator. All right. So to get a trustworthy estimate of an unknown population parameter, start by using a statistic that is an unbiased estimator. Okay? So unfortunately, using an unbiased estimator doesn't guarantee that the value of your statistic will be close to the actual parameter value. We prefer statistics that vary less from the actual parameter value. So, for example, right, because up here, say this is my sampling distribution of size of whatever with my sample size n is 100, right? If I took the mean of this, the mean of my sampling proportions, that would still equal p. All right, so it is an unbiased estimator. P-hat is an unbiased estimator. However, each one of these is a different sample. And because of sampling variability, they could be very spread out. So if I got like this specific value for p-hat, that's not necessarily close to what p is equal to. It is an unbiased estimator when I take the mean of it. However, that specific sample is not necessarily close. So instead, we prefer statistics that vary less, because if they vary less, then my p-hat's automatically going to be closer, right? Think about this. The smallest p-hat here is, let's say 0.23, all the way up to 0.5. Versus, if I could get it, I could shrink the variability from 0.33 to 0.43. I've cut off quite a bit of variability in my data. The question is, how do we actually minimize that variability? Well, we talked about it before, but the way to minimize your variability is to increase your sample size. So the only thing different between these two graphs, each dot up here is the sample proportion for a sample size of 100. And down here, each of them is a sample size of 1,000. But besides that, it's the same distribution. So just increasing the sample size will decrease your variability. Right? We prefer statistics that vary less from the actual parameter value. Large random samples tend to produce estimators that are closer to the true population value. So, in many cases, it is obvious which statistics should be used as an estimator of a population parameter. If we want to estimate a population proportion P, we should use the sample proportion P hat. Okay. If we want to estimate a population mean, which is mu, we should use the sample mean x. Okay. But either way, if we're using mean or p hat, or if we're looking for the mean or the proportion, so we're using p hat or x bar, the better way to minimize the variability is to increase that sample size. To decide which estimator to use when there are several reasonable estimating choices, consider both bias and variability. All right. And we have this little target thing that you might have seen before. All right. So bias means that our sample statistic does not center on the population parameter. In other words, our estimators are not accurate. Think about that range one, right? That is an unbiased estimator, or it is a biased estimator, I'm sorry. So it narrowed down on a value that wasn't close to the true proportion or the true population, right? Our sample range mean gave us 3.67, while the parameter range or the population range was 7. So quite a bit off, right? So for example, that would be these first two, right? Look at if these are all my data points, they are not close to the center. These are not close to the center. So they are not honing in on the true value. Right? High variability means that repeated samples do not give very similar results. In other words, our estimates are not very precise. So the data is very spread out. All right. So think about here, the data is pretty spread out. It's pretty honed in on it. So it's not biased, or in other words, it is accurate, right? These data points do kind of fall around the center. However, they're very spread out. So it's not very precise. This one, again, the data points are spread out again. So it's not very precise. And this one is also not accurate. This clump of data is not accurate. It's not close to the center. However, it's pretty precise. Those points are all very close together. So then lastly, obviously what we want to go for is very precise and very accurate. So this bottom one does achieve that. It achieves the accuracy because all those data points are close to the center, all right, which is how you define accuracy, close to what you're trying to estimate. And then they are very precise because they don't vary out much. They're not very spread out, so it is a very precise estimate. So this is very important. Make sure to understand the difference between accuracy and precision. Accurate means you are close to the data value. Precise means you are there's not a lot of variability. Right, so make sure you know the difference when writing responses on an AP statistics exams. Many students use accurate when they really mean precise. For example, a response that says increasing the sample size will make an estimator more accurate is incorrect. It should say that increasing the sample size will make an estimator more precise because it lowers variability. If you can't remember the term, don't use it. Just explain what you mean instead. So instead, what I would say is increasing the sample size decreases the variability. That is a totally fine thing to say. I don't even talk about the word precise or accurate, so I can't mess it up. I just explain what's going on. Increase the sample size, decrease the variability. Simple as that. All right. And those are your learning targets for 7.1. All right. Hope you enjoyed.